Right now, while you're listening to this, a sunspot, AR4294, 10 times wider than our planet, is staring directly at Earth, rotating into the perfect firing position. Scientists are comparing this sunspot to the 1859 Carrington Event that set telegraph wires ablaze and painted auroras across the tropics. But here's what should genuinely unsettle you. While smaller regions nearby have been exploding with X-class fury, launching billion-ton plasma bombs at 2 million miles per hour, AR4294 has gone silent. Physicists call it the coiled-spring paradox. The bigger and quieter it gets, the more catastrophic the release. Stay with me, because by the end, you'll understand why this silence might be the worst possible news, and why our models completely missed it. You'll want to stay with us as AR4294 continues its slow rotation across the solar disk, and the observations keep streaming in from spacecraft watching its every move. Subscribe and follow along, because each new magnetogram, each updated forecast, brings us closer to understanding whether this is a statistical fluke or a symptom of something big about to hit. Now, let's settle in and unravel this solar mystery together. Right now, at this very moment, a monster is staring at us. It's roughly the size of India. It contains enough magnetic energy to power human civilization for 1 million years. And for the past several days, it's been doing the one thing that terrifies solar physicists more than anything else. It's been silent. Let me paint you a picture. On the surface of our sun, rotating into perfect alignment with Earth, sits a sunspot complex so enormous that astronomers had to give it 3 separate designation numbers because their classification system couldn't handle its scale. AR4294, AR4296, AR4298. 3 names for what is essentially one monstrous, sprawling wound on the face of our star. When scientists overlay images of this beast with the famous sunspot from the 1859 Carrington Event, the one that set telegraph offices on fire and painted auroras across the Caribbean, they notice something unsettling. AR4294 is bigger. The numbers are genuinely staggering. This thing spans approximately 130,000 kilometers across. That's 10 times the diameter of Earth. If you could place our entire planet inside this sunspot, you'd fit 10 of them, side by side, and still have room to spare. In technical terms, it occupies roughly 2,300 millionths of the solar hemisphere. In human terms, imagine a dark continent carved into the surface of the sun, visible even through eclipse glasses if you were foolish enough to look directly. But here's where things get interesting. In the way that noticing smoke in your house gets interesting. This sunspot complex is classified as beta gamma delta. For those of you who don't speak solar physics, let me translate. Beta means we've got multiple sunspots with opposite magnetic polarities. Gamma means those opposite polarities are tangled together in the same region. Delta, that last designation, is the kicker. Delta means magnetic field lines of opposite polarity are pressed directly against each other. Imagine 2 massive, invisible magnets, North Pole against South Pole, straining against each other across a planetary scale. This configuration is the solar equivalent of a loaded gun. Statistically, regions with this magnetic architecture have the highest probability of producing X-class flares, the most powerful category of solar eruptions we measure. But AR4294 isn't following the script. It should be exploding. The models say it should be exploding. And yet, for days now, the core of this region has remained disturbingly, unnervingly quiet. The neighborhood around AR4294 has been anything but quiet. On December 1st, 2025, a neighboring active region, AR4299, unleashed an X1.9 flare. That's a major solar flare, the kind that causes immediate high-frequency radio blackouts across entire continents. Australia and Southeast Asia lost HF communications. Ham radio operators went silent. Aviation frequencies crackled and died. 5 days later, on December 6th, the same region fired off an M8.1 flare, launching a coronal mass ejection, a billion-ton cloud of magnetized plasma, directly at Earth. The National Oceanic and Atmospheric Administration modeled that CME traveling at approximately 1,143 kilometers per second. That's over 2 million miles per hour, fast enough to cross the Earth-Sun distance in roughly 40 hours. NOAA issued a G3 geomagnetic storm watch, categorized as strong on their 5-tier scale, with predicted arrival around December 9th. G3 storms can cause intermittent satellite navigation issues, increased drag on low Earth orbit satellites, and power grid fluctuations. Auroras appear as far south as Illinois and Oregon. But here's the thing that keeps solar physicists awake at night. All of that chaos came from the neighboring regions. AR4294, the actual monster, the one with the Delta classification and the continental scale, has been mostly quiet. And in solar physics, silence from a region like this isn't reassuring. It's terrifying. Think of it this way. Magnetic energy in the sun builds up over time through a process called magnetic shear. Field lines twist around each other, storing energy the way a spring stores energy when you compress it. Imagine a thick rubber band twisted tighter and tighter. At first, nothing happens. The rubber band just sits there, holding all that potential energy. But eventually, inevitably, something gives. The magnetic field lines, tangled and compressed beyond their breaking point, suddenly reconnect in a process called magnetic reconnection, and all that stored energy explodes outward in a single catastrophic release. AR4294 is the rubber band, and we're watching it twist tighter. The sun rotates, carrying active regions across its face from our perspective. There's a window of opportunity, or, if you prefer, a window of danger, when a region is optimally positioned to send coronal mass ejections our way. That window is roughly centered on the solar disk and extends maybe 30 degrees on either side. AR4294 rotated into that window days ago. It's facing us now. If it erupts, if it finally releases all that pent-up magnetic energy, we're directly in the line of fire. What does that actually mean for us? Auroras are the pretty part, the tourist attraction. The real concern is what happens to infrastructure. High-frequency radio communications can be completely blacked out for hours. GPS signals degrade. Satellites experience increased atmospheric drag and electrical anomalies. Astronauts shelter in more heavily shielded modules to avoid radiation exposure. And if the storm is strong enough, geomagnetically induced currents can flow through power grids, causing voltage instability and, in extreme cases, transformer damage. For now, AR4294 remains quiet, but the clock is ticking. In a few days, this region will rotate past the optimal geo-effective longitude. We have a narrow window where this thing is pointed right at us, and with every hour that passes without an eruption, the statistical likelihood of a major event doesn't decrease. If anything, the longer it stays quiet, the more energy it might be storing. Because if AR4294's timing is strange, if its sheer scale is outside the normal bounds of what we expect from Solar Cycle 25, then maybe the models we've been using to predict solar activity are missing something fundamental. Our sun follows patterns, rhythms beaten out over centuries of observation. We've mapped these patterns into something called the solar cycle, an 11-year period during which solar activity rises from minimum to maximum and back again. We build forecasts, we make predictions, we plan satellite launches and power grid maintenance schedules around the expected quiet and active phases. AR4294, if you're keeping score, was not in the forecast. Solar Cycle 25 officially began in December 2019. Forecasts from NOAA and other agencies predicted a relatively mild cycle, with solar maximum expected sometime in 2024 or early 2025. The predictions were decent. Activity did peak roughly when expected, but those same models also suggested that by late 2025, activity should be winding down. Sunspot emergence should be slowing. Instead, we got AR4294, a gargantuan, complex delta configuration monster emerging late in the cycle, well after the statistical peak. Let me explain why this is weird. Sunspots emerge when loops of magnetic flux, generated deep in the sun's interior, bob up through the photosphere. Early in a solar cycle, these flux ropes emerge at higher latitudes, around 30 or 40 degrees north or south of the solar equator. As the cycle progresses, new spots emerge closer to the equator. By the time a cycle is winding down, flux emergence is concentrated near the equator, and the spots that do emerge tend to be smaller, less complex, less magnetically active. Large, complex, delta configuration regions like AR4294 are supposed to appear near solar maximum, not in the declining phase. And there's another oddity. NOAA had to split this region into 3 separate active region numbers because the standard classification system assumes each region is a discrete entity. AR4294 is so large, so sprawling, that it doesn't fit neatly into that framework. Multiple cores, all tangled together in a single vast complex spanning 2,300 millionths of the solar hemisphere. A typical large sunspot might cover 50 to 100 millionths. AR4294 is roughly 20 to 40 times larger in area. There are reports, as yet unconfirmed but tantalizing, that NASA's Perseverance rover on Mars detected signatures from this active region when it was still on the far side of the Sun, before it rotated into Earth's view. If true, that's remarkable. Farside detection gives us advance warning. Right now, we're mostly blind to what's happening on the far side of the Sun. The problem is, it also means this region was active and detectable from interplanetary distances before we even knew it existed. So why do our models struggle with this? Our models of solar activity are built on a combination of statistical patterns and physics-based simulations. The statistical side works well for predicting the general shape of a cycle, but predicting individual active regions, especially extreme outliers, requires understanding the subsurface dynamics of magnetic flux emergence. And that's where the physics gets murky. The Sun's magnetic field is generated by a dynamo process deep in its interior, probably near the boundary between the radiative zone and the convective zone. Differential rotation stretches and twists magnetic field lines, storing energy. Convection tangles things further. Eventually, buoyant loops of magnetic flux rise and emerge at the photosphere as sunspot pairs. The problem is, we don't know exactly where that flux is stored before it emerges, how long it stays down there twisting, or what triggers the final eruption. It's like trying to predict where and when a bubble will rise in a pot of boiling water. Most sunspot emergence events are like raindrops in a storm. Individually unpredictable, but statistically, you can forecast how many will fall in an hour. AR4294 is like a hailstone the size of a basketball crashing through your windshield. The storm models didn't predict it, because events like this live in the extreme tail of the distribution, where statistical methods break down, and you need to understand the underlying physics at a much deeper level. And this has consequences. If our models can't predict large, late cycle active regions, then our forecasting windows shrink. Agencies can tell you the general level of solar activity 6 months from now, but they can't tell you whether a civilization-threatening monster sunspot will pop up next week. That forces us to rely more heavily on real-time monitoring. By the time we see a region like AR4294, it's already rotated into view. We get maybe 10 days of warning before it rotates off the visible disk again. There's a darker narrative lurking here, and I'll be upfront that this is conjecture. Some observers have asked whether space weather agencies might downplay extreme solar activity risks to avoid triggering market panic. Modern economies are so dependent on satellite infrastructure and reliable power grids that an honest assessment of a Carrington-level threat could cause financial disruptions. Now, to be clear, there's no confirmed evidence that agencies are deliberately withholding alarming forecasts. Their watch statements are measured and professional, but the question nags. For now, the official stance remains cautious optimism. Space weather forecasting has improved dramatically. Real-time data streams from multiple spacecraft provide unprecedented situational awareness. The system works, they say, as long as everyone stays calm. But playbooks are written for scenarios we've encountered before. We've never stress-tested modern civilization against a solar storm of Carrington magnitude. And if AR4294 represents something outside the envelope of normal solar cycle behavior, then maybe our playbooks are incomplete. Because if models fail and silence grows, we have to ask a harder question. Could this be a rehearsal for something far larger than anything in our recorded history? Tree rings say yes, and that brings us to the Miyaki problem. Tree rings whisper secrets. Buried deep in the annual growth layers of ancient bristlecone pines and European oaks are records of cosmic violence that make the Carrington Event look like a firecracker. These are called Miyaki events, named after the Japanese physicist who identified the first clear signature in 2012. They are sudden, dramatic spikes in atmospheric carbon-14, isotopes produced when high-energy cosmic rays or solar particles slam into nitrogen and oxygen in the upper atmosphere. And the spikes are enormous, implying radiation levels 10 to 20 times greater than anything we've measured in the modern era. The most famous examples occurred in 774 CE and 993 CE. Tree ring analyses from samples around the world show the same signal: a sharp jump in carbon-14 concentration over the course of a single year, far too rapid to be explained by gradual cosmic ray variations. The 774 event shows an increase of roughly 12 parts per thousand in radiocarbon content, a signature so strong that it's visible in trees from Japan to Germany to California. But here's the catch: we don't know for certain what caused these events. The leading hypothesis is an extreme solar energetic particle event, essentially a solar flare and coronal mass ejection on a scale that dwarfs anything in our recorded history. But other possibilities exist. A gamma ray burst from a nearby supernova, or a massive cometary impact on the sun. The honest answer is that we're working from tree rings and ice cores, not direct observations. We see the effect, but the cause remains debatable. What we do know is that events of this magnitude happen. They've happened before. They'll happen again. And what would a Miyaki-class event actually do to us? A Carrington-level coronal mass ejection today would cause widespread auroras, significant geomagnetic storm impacts, and regional power grid disruptions. Recovery would be measured in days to weeks. A Miyaki-class event would be orders of magnitude worse. We're talking about global satellite sterilization. Every satellite in low Earth orbit, every GPS constellation, every communications relay hit simultaneously by radiation. They were not designed to survive. Within hours, you'd lose GPS timing signals that underpin everything from financial markets to power grid synchronization. You'd lose satellite communications, weather forecasting satellites, and early warning systems. On the ground, geomagnetically induced currents would flow through power transmission lines at unprecedented levels. Extra high voltage transformers would saturate, their cores overheating. You can't just order a replacement EHV transformer quickly. These are bespoke pieces of equipment with lead times measured in months or years. Lose enough of them simultaneously, and you're looking at regional blackouts lasting months, maybe longer. Then there's the radiation risk. Astronauts would be exposed to doses potentially exceeding their career limits in hours. Airlines would ground polar flights immediately. Frequent flyers and crew on polar routes would receive measurable radiation doses, adding to lifetime exposure and increasing cancer risk. The psychological and social impacts might be the hardest to quantify. Imagine waking up to discover that GPS doesn't work. Your phone has no signal. The power goes out, and utility companies are saying it could be weeks or months before service is restored. ATMs don't work. Credit card terminals don't work. Supply chains freeze. Hospitals switch to backup generators, but fuel supplies are limited. Within 72 hours, you're looking at cascading failures across every system that depends on electricity. It's not a sudden collapse into chaos. It's a slow, grinding erosion of the invisible infrastructure that keeps modern life humming along. Now, to be absolutely clear, no agency is predicting a Miyaki-class event from AR4294. NOAA's current watch is for a G3 storm, which is serious but manageable. The difference between a G3 and a Miyake-level event is like the difference between a thunderstorm and a Category 5 hurricane. But the fact that AR4294 exists, that it's larger than models predicted, forces us to ask uncomfortable questions. If our models missed this, what else might they be missing? Let's ground this in history. The 1859 Carrington Event is our benchmark. Auroras were visible as far south as the Caribbean. Telegraph systems sparked and caught fire. It was spectacular and terrifying. But Carrington happened when the only long-distance electrical infrastructure was the telegraph. Imagine the same event today. The cascading failures would be exponentially worse. Now scale that up by a factor of 10 or 20 to Miyake levels, and you're looking at a civilization-altering event. So what would it take for AR4294 to produce something approaching Miyake scale? You'd need an ultra-fast coronal mass ejection, something traveling at 2,000 kilometers per second or faster. You'd need the CME's magnetic field orientation to align with Earth's in the worst possible way. You'd need the magnetosphere already in a preconditioned, unstable state. And you'd need high-energy solar particle acceleration, producing massive proton fluxes. None of those conditions are currently confirmed for AR4294, but the region has the magnetic complexity to make some of them plausible, because Miyake events are not theoretical. They happened. 774. 993. The sun is capable of this level of violence. The only reason we think of solar storms as manageable is that we've only been measuring them with modern instruments for a few decades. That's a tiny sample. We're like meteorologists who've only seen thunderstorms trying to forecast a tornado. The data says tornadoes exist, but we've never seen one. And now there's a storm forming that doesn't look like anything in our playbook. That's AR4294. In 1989, on a cold March night, the entire province of Quebec went dark in 92 seconds. 6 million people lost power. The cause was a geomagnetic storm, rated G5, the most severe category. The storm was intense, but by Carrington standards, it was moderate. And yet, it crippled Hydro-Quebec in less than 2 minutes. That should terrify you. Let me explain how this works. When a coronal mass ejection slams into Earth's magnetosphere, it compresses and distorts the magnetic field. This creates fluctuations in the geomagnetic field at ground level. A changing magnetic field induces an electric current in any conductor. Power transmission lines, stretching for hundreds of kilometers, are perfect conductors for geomagnetically induced currents. When the geomagnetic field fluctuates during a solar storm, it drives slow, quasi-DC currents through the power grid. Transformers are designed to handle alternating current. When you introduce a DC component, it causes the transformer core to saturate. The core can't handle the magnetic flux density, and it stops effectively confining the magnetic field. This causes massive increases in reactive power consumption and, most critically, heating. The transformer overheats. Protective relays might trip it offline before permanent damage occurs. But if the current is strong enough or sustained enough, the transformer can fail catastrophically. Insulation breaks down. Windings short circuit. In extreme cases, the transformer can physically rupture and catch fire. And once a large extra high voltage transformer is destroyed, it's not a quick fix. We're talking about equipment that can weigh hundreds of tons, cost millions of dollars, and require months to manufacture. Quebec in 1989 lost power for 9 hours. They were lucky. But imagine a Carrington-level storm, or worse, a Miyaki-class event. Imagine currents not just strong enough to trip relays, but strong enough to destroy transformers faster than operators can isolate them. Economic cost estimates for a Carrington-scale storm today range between $1 and $2 trillion. The most expensive natural disaster in U.S. history, Hurricane Katrina, caused roughly $125 billion in damage. A severe solar storm could be an order of magnitude worse. So why haven't we fixed this? Why haven't power companies invested in hardening their grids? The answer is economics. Hardening the grid is expensive, running into billions of dollars. Utilities operate in regulated markets where they can only charge rates approved by regulators. If a utility proposes to spend billions hardening the grid against a once-in-a-century solar storm, regulators often balk. Ratepayers don't want higher electricity bills for protection against an event that might never happen. And so the investment doesn't get made. It's the pay now or maybe never problem. There are mitigations that exist and are underused. GIC blocking capacitors can be installed at transformer neutral points. Neutral blocking devices can be deployed strategically. Operational procedures, like reconfiguring transmission lines during storms to reduce exposure, can help. Some utilities, particularly in Scandinavia, have invested in these measures. But adoption is uneven. Some utilities have taken the threat seriously. Others have done the minimum required. A grid collapse doesn't happen in isolation. Power is the foundation of modern infrastructure. Lose power, and you lose everything else in a cascading sequence. Water treatment plants rely on electric pumps. Without power, water pressure drops. Sewage treatment plants fail. Fuel distribution networks shut down. Telecommunications infrastructure, cell towers, and fiber optic repeaters rely on backup batteries that last maybe 8 to 12 hours. Without power, communications go dark. Supply chains freeze because modern logistics depend on real-time GPS tracking. Within 72 hours of a major grid collapse, you're looking at food shortages, hospitals running on limited generator capacity, and civil authorities struggling to coordinate response. And here's the political angle, which I need to tread carefully with because it's speculative. There's a hypothesis that governments downplay the severity of space weather risks to avoid triggering financial market panic. If a major agency publicly stated that a Carrington Plus event had a 10 or 20% chance in the next decade, what would happen? Stock markets would react. Insurance companies would reassess risk models. Utilities would face shareholder lawsuits. Now, is there actual evidence that agencies are deliberately soft-pedaling their forecasts? No. No AA's public statements are professional and appropriately cautious, but the question remains. At what point does cautious communication cross into downplaying risk to maintain social stability? For now, the official message remains that space weather is a manageable risk. Agencies emphasize that modern forecasting gives us advance warning, that grid operators have protocols, and that civilization would survive. And maybe they're right. Maybe with proper preparation, we can weather even a severe solar storm. But maybe is a dangerous word to hang the future of technological civilization on. AR4294 might be a fluke, a one-off statistical outlier that just happened to emerge late in solar cycle 25. Or it might be a symptom, a visible manifestation of something stranger happening beneath the surface of the sun. Because the sun is not behaving entirely as expected lately, and AR4294 is just the most dramatic example. There are other anomalies, quieter ones, that suggest the solar dynamo, the engine that generates the sun's magnetic field deep in its interior, might be doing something unusual. And if the sun's dynamo is shifting into a different mode, then all bets are off regarding what we should expect in the years to come. Let's start with an odd coincidence that's probably not related, but is too interesting to ignore. Earth's magnetic North Pole has been drifting unusually fast over the past few decades, accelerating from about 15 kilometers per year in the early 2000s to roughly 50 to 60 kilometers per year recently. It's migrated from northern Canada towards Siberia, crossing the international dateline and showing no signs of slowing down. Now, Earth's magnetic field is generated by the motion of molten iron in the outer core, thousands of kilometers beneath our feet, and it's completely independent of the sun's magnetic field. There's no direct causal connection between solar activity and Earth's pole drift. And yet, it's curious that both systems, Earth's geomagnetic field and the sun's magnetic field, seem to be exhibiting unusual behavior at roughly the same time. Is it coincidence? Almost certainly. But it's the kind of coincidence that makes you wonder whether there's some larger solar system scale magnetic phenomenon at play that we don't yet understand. Or maybe I'm seeing patterns in noise. Either way, it's an interesting question for future research. More concretely, there have been reports, though I'll emphasize these need careful verification, that helioseismology studies in 2025 have detected unusual subsurface flows in the sun. Helioseismology is the study of oscillations and waves in the sun's interior, analogous to how seismology studies earthquakes to map Earth's interior structure. By analyzing oscillation patterns on the sun's surface, scientists can infer things about the speed and direction of plasma flows deep inside. Some recent studies, if the reports are accurate, have noted asymmetries between the northern and southern hemispheres in terms of subsurface flow patterns and magnetic flux emergence. If confirmed, that's genuinely interesting, because the solar dynamo is supposed to be roughly symmetric. An asymmetry suggests that something is off balance, that the dynamo is not operating in its typical smooth mode. And that could potentially explain why we're seeing unexpected late cycle activity like AR4294. To understand why this matters, we need to talk about how the solar dynamo works, at least as far as we understand it. The sun's magnetic field is generated by a process involving differential rotation and convection. Differential rotation, the fact that the equator spins faster than the poles, stretches out magnetic field lines, converting poloidal field, which runs from pole to pole, into toroidal field, which wraps around the sun in bands parallel to the equator. This toroidal field is stored deep in the sun, probably near the tachocline, the boundary between the radiative and convective zones. When the toroidal field becomes strong enough and buoyant enough, loops of it rise through the convection zone and emerge at the surface as sunspot pairs. Meanwhile, convective motions near the surface twist and tangle the magnetic field, regenerating poloidal field from toroidal field and completing the cycle. This is called the Babcock-Leighton dynamo mechanism, and it's the leading model for how the sun generates its 11-year magnetic cycle. But here's the catch. This model is based on mean field theory, which averages over the turbulent, chaotic convective motions happening in the sun's outer layers. It works reasonably well for predicting the general shape of the solar cycle, but it struggles with details. It can't tell you exactly when a specific sunspot will emerge, or how large it will be, or whether it will have a delta configuration. Those details depend on subsurface turbulence, magnetic instabilities, and nonlinear interactions that are extremely difficult to model. It's like trying to predict the exact trajectory of a leaf falling from a tree in a windstorm. You can describe the general process, but the specifics are governed by chaos. Now, let's speculate carefully about 3 possible scenarios that could explain AR4294 and other recent oddities. The first scenario is toroidal field instability. The idea here is that deep belts of toroidal magnetic field stored near the tachocline can sometimes become unstable. Instead of rising smoothly and emerging as typical sunspots, a large section of the toroidal belt slips upward en masse, producing an unusually large coherent active region. This could explain AR4294's size and coherence. If it's a chunk of deep toroidal field that erupted all at once, rather than a typical emergence of a single flux rope, that would account for its exceptional scale. Evidence for this would include detailed magnetic topology measurements and comparisons with dynamo simulations, but as of now, it's just a hypothesis. The second scenario involves overshoot layer turbulence. The overshoot layer is a thin region just below the convection zone, where downward convective flows overshoot into the stable radiative zone before bouncing back. This layer is thought to be a key site for magnetic field storage and amplification. If turbulence in the overshoot layer is unusually strong, it could kick up larger than normal flux ropes. Think of it like turbulence in water, kicking up bigger waves. Again, this is speculative, but it's consistent with the idea that AR4294 emerged from some kind of subsurface instability rather than the normal flux emergence process. The third scenario is dynamo phase slippage. The sun's dynamo operates with a roughly 11-year periodicity, but the exact timing and amplitude of each cycle vary. Some solar cycles are strong, some are weak. There's also evidence of longer-term modulations, like the Gleisberg cycle, which is an 80 to 100-year variation in solar cycle amplitude. If the dynamo's phasing is slipping, if there's some kind of internal resonance or instability that's causing the normal 11-year rhythm to hiccup, you might get unexpected bursts of activity outside the usual cycle phase. AR4294, in this view, is a symptom of the dynamo briefly jumping to a different rhythm before settling back. It's a compelling idea, but proving it would require decades of observations and detailed dynamo modeling. All 3 scenarios are theoretical. None are proven, but they're scientifically plausible, and they highlight a fundamental truth. The sun is vastly more complex than our models capture. We're working with 100 years of direct observations, trying to understand a system with timescales ranging from minutes, in the case of flares, to millions of years, in the case of the sun's overall magnetic evolution. We're extrapolating from a tiny sample, and when something like AR4294 appears, it reminds us just how limited that sample really is. And here's why that matters. If the sun is capable of producing late-cycle monsters like AR4294 without warning, then our risk assessments for space weather are probably too optimistic. We base those assessments on historical data and statistical models that assume the sun's behavior is stationary, that the distribution of sunspot sizes and flare energies doesn't change over time. But what if it does? What if the sun goes through epochs where extreme events are more common, followed by epochs where they're rare? The Maunder minimum, a period from 1645 to 1715, when sunspot activity nearly disappeared, suggests that the sun's behavior is not always regular. Grand minima, like the Maunder, and possibly grand maxima, periods of unusually high activity, are part of the sun's long-term variability. If we're entering a period of higher variability, or if the dynamo is in some kind of transitional state, then the statistical models we rely on might be fundamentally miscalibrated. The good news, if you can call it that, is that we have better tools now for monitoring the sun than ever before. Farside imaging using helioseismology or future spacecraft at the L5 Lagrange point can give us advance warning of active regions before they rotate into Earth's view. That was the tantalizing promise of the Perseverance detection claim, if verified. More spacecraft, better instruments, and improved computational models are all in the pipeline. We're getting better at this. But we're also running a race against time. Every day that passes without a major extreme solar event is a day where we get complacent, where budgets for space weather monitoring get cut, where grid hardening projects get delayed. And the sun doesn't care about our complacency. It operates on its own timescales, and when it decides to remind us who's boss, it does so without warning, without mercy, and without concern for our infrastructure, our economy, or our carefully constructed models. AR4294 is still out there, rotating slowly across the solar disk. In a few days, it'll rotate off the Earth-facing hemisphere and disappear from our direct view. Maybe it'll go quietly, just a brief scare, a statistical blip, or maybe, just before it rotates out of sight, it'll unleash the event we've been nervously anticipating, a massive X-class flare and a fast CME that reminds us why we monitor the sun so obsessively in the first place. Either way, it's a reminder. The sun is not our friend. It's a roiling, churning ball of plasma and magnetic chaos, and we live at its mercy. And while the sun keeps us on edge, wondering when and if the monster will wake, science elsewhere is also showing cracks in our models. Particle physics and artificial intelligence are both rewriting assumptions this year, forcing us to confront the possibility that we understand the universe and our own creations far less well than we thought. And that takes us beyond the sun, into the colliders and the algorithms that are reshaping what we thought we knew. If particles refuse to behave, and stars refuse to behave, maybe our models are due for a reboot. Because in 2025, deep beneath the Franco-Swiss border, physicists at the Large Hadron Collider found something that shouldn't exist, or at least shouldn't exist in the neat, orderly way the standard model of particle physics predicts. They found CP violation in baryons. And if you're not a particle physicist, that probably sounds like meaningless jargon. Let me translate. What they found is proof that the universe has a preference, a tiny, measurable bias in the way certain particles decay. And that bias, multiplied across 13.8 billion years of cosmic evolution, might be the only reason we exist at all. Here's the backstory. One of the great mysteries of cosmology is the matter-antimatter asymmetry. In the first moments after the Big Bang, equal amounts of matter and antimatter should have been created. Particles and their antiparticles. Protons and antiprotons. Electrons and positrons. All popping into existence in perfectly balanced pairs. And when matter meets antimatter, they annihilate, converting back into pure energy. If the universe started with perfect symmetry, matter and antimatter should have annihilated each other completely, leaving nothing but photons and a cold, empty cosmos. But obviously that didn't happen. We're here. Stars are here. Galaxies are here. For some reason, the early universe produced slightly more matter than antimatter, maybe one extra matter particle for every billion matter-antimatter pairs. That tiny excess survived the annihilation epoch and became everything we see around us. The question is, why? What broke the symmetry? What process favored matter over antimatter? This is where CP violation comes in. CP stands for charge parity. It's a symmetry in physics that says if you swap a particle for its antiparticle, that's the C part, charge conjugation, and you flip it in a mirror, that's the P part, parity inversion, the laws of physics should look the same. For most processes, CP symmetry holds. But in 1964, physicists discovered that certain weak force decays of particles called kaons violated CP symmetry. The decay rates for kaons and their antiparticle counterparts were slightly different. That was the first crack in the symmetry. Later, CP violation was also observed in B mesons, particles containing bottom quarks. The standard model predicts CP violation through something called the CKM matrix, a mathematical object that describes how quarks transform during weak interactions. and for a long time, the CP violation we observed in mesons was broadly consistent with the CKM predictions. Not enough to explain the matter-antimatter asymmetry, but consistent with the framework. Then, in 2025, the LHCb experiment at CERN announced something new. They'd observed CP violation in Beauty lambda baryons. Baryons are particles made of three quarks, like protons and neutrons. Beauty lambda baryons contain a bottom quark, plus two lighter quarks. And when these baryons decay, the rate at which they decay into certain final states is different from the rate at which their antiparticle counterparts decay into the corresponding antistates. The asymmetry measured was 2.45%, and the statistical significance was 5.2 sigma, which in particle physics terms means it's a rock-solid result. This is the first time CP violation has been observed in baryons. It's a new channel, a new pathway, through which the universe can exhibit asymmetry. Why does this matter? Because every new source of CP violation we find expands the toolkit nature has for generating the matter-antimatter asymmetry. The CKM mechanism in the standard model isn't enough on its own to explain why the universe is made of matter. The amount of CP violation it predicts is too small by several orders of magnitude. So physicists have long suspected there must be additional sources of CP violation beyond the standard model, lurking in some new physics we haven't discovered yet. Finding CP violation in baryons doesn't solve the problem, but it points us in interesting directions. It suggests that baryon decays, which were largely ignored in earlier matter-antimatter asymmetry calculations, might play a role. It opens up new avenues for theoretical models, new ways to connect particle physics experiments to the cosmic question of why we exist. And here's where it ties back to our broader theme. The LHCb result is an example of nature refusing to fit neatly into our existing models. The standard model predicted CP violation in mesons, and we found it, but it didn't predict with any confidence that we'd find it in baryons at this level. The fact that we did means our understanding of quark dynamics, weak interactions, and the subtle asymmetries governing particle decays is incomplete. There are effects happening that our models didn't fully capture. Just like AR4294 is a sunspot our solar cycle models didn't predict, the baryon CP violation is a decay asymmetry our particle physics models didn't confidently anticipate. In both cases, nature is showing us that our frameworks, while useful, are approximate, limited, and subject to surprises. The narrative here is compelling. The universe shows a crack in one place, a baryon that decays asymmetrically. The sun shows a crack in another, a sunspot that appears when and where it shouldn't. Is this coincidence, or is it a broader sign of our model's fragility? Now, to be clear, that's a rhetorical question, a narrative device. There's no direct connection between solar magnetic field dynamics and baryon CP violation. They operate in entirely different physical regimes, but the parallel is philosophically interesting. Both phenomena remind us that the natural world is vastly more complex than the simplified models we use to navigate it. Both show that tail events, outliers, the things that live in the less than 1% probability zone, are where the most interesting physics happens. And both challenge us to be humble about what we think we know. Particle physicists are conservative by training. They don't leap to grand conclusions based on a single result. The LHCb CP violation measurement is statistically solid, but it's one data point. To really understand what's going on, they need more measurements, from more decay channels, from more experiments. They need to map out the full landscape of CP violation in baryons, test whether it fits into extended versions of the standard model, or whether it points to something entirely new. This is incremental science, the kind that takes decades, but it's also thrilling science, because every new measurement has the potential to crack open a new layer of reality. And there's a practical angle here, although it's a long-term one. Understanding CP violation and the matter-antimatter asymmetry is not just an academic exercise. It's fundamental to understanding why the universe exists in its current form. If we ever develop technologies capable of manipulating antimatter at scale, say for propulsion or energy generation, understanding the subtle asymmetries governing particle interactions will be critical. That's science fiction today, but so was splitting the atom 100 years ago. The point is that fundamental physics, even the stuff that seems impossibly abstract, has a way of becoming practical technology given enough time. But for now, the takeaway is simpler. The universe is weird. Particles decay asymmetrically. The sun spits out late-cycle monster sunspots. Our models capture the broad strokes, but they miss the details, the outliers, the things that don't fit the tidy narratives we've constructed. And while particle physicists chase the smallest asymmetries in their detectors, another field is rewriting how we chase anomalies themselves. Artificial intelligence, the tool we've built to help us make sense of the flood of data pouring in from colliders and telescopes and solar observatories, is itself becoming unpredictable. And that's where we turn next, to the machine intelligence shockwave of 2025 and the question of whether we can trust the algorithms we're increasingly relying on to understand the world. We built prediction engines to help us see patterns we'd miss on our own. But the engines we've built are changing faster than we can track. In 2025, artificial intelligence crossed a threshold that most people didn't notice, but that researchers found both exhilarating and unnerving. We're now deploying autonomous multi-agent AI systems that don't just respond to prompts. They plan, they iterate, they coordinate with each other, and they're beginning to automate the process of scientific discovery itself. Multi-agent AI means multiple AI agents, each with specific roles, communicating with each other to solve complex problems. One agent might propose hypotheses, another designs experiments, a third analyzes results and updates the hypothesis, a fourth prioritizes which experiments to run next. They form a collaborative network, a kind of artificial research team, and they iterate through this cycle autonomously. The leap in capability is enormous. In 2025, research groups demonstrated systems where autonomous AI agents conducted entire scientific workflows, from literature review to hypothesis generation, to experimental design, to data analysis, with minimal human oversight. These systems haven't discovered new laws of physics yet, but they've successfully replicated known results, identified patterns in large datasets that human researchers missed, and proposed novel experimental approaches. Within a few years, maybe a decade, we'll have AI systems capable of conducting large portions of scientific research autonomously. Now let's bring this back to solar forecasting. Predicting solar flares and coronal mass ejections is data intensive. We have continuous streams of imagery and magnetic field measurements from spacecraft like the Solar Dynamics Observatory. The data volume is staggering, and the challenge is to make actionable predictions. When will a flare occur? How strong will it be? Will it launch a CME? AI models have been applied to this problem for years. Machine learning algorithms can predict flares with reasonable accuracy, but they struggle with rare events, the tail of the distribution. X-class flares are uncommon. Major CMEs directed at Earth are rarer still, and something like a Miyaki class event has never been observed in the modern era, so there's no training data. AI models are data hungry. They learn patterns from examples. If there are no examples, the models have nothing to learn from. Multi-agent systems offer a potential way forward. Instead of training a single model on historical data, you deploy multiple agents with different approaches. One agent uses physics-based models. Another uses statistical models. A third uses image recognition. A fourth acts as a metacognitive overseer, weighing the outputs and synthesizing a consensus forecast. By combining multiple approaches, you get more robust predictions. But here's the speculative scenario. Imagine a near-future space weather center where an autonomous, multi-agent AI system runs continuously, monitoring solar data in real time. It doesn't just forecast, it runs scenario simulations. What if AR4294 fires an X10 flare in the next 6 hours? What would the CME trajectory be? The AI runs thousands of what-if scenarios every hour, and it interfaces directly with automated grid control systems. If the probability of a severe storm crosses a threshold, the AI autonomously triggers protective measures. That's the dream scenario. The reality is more complicated. First, there's the trust problem. How confident can you be in an AI system's predictions, especially for rare events? If the AI recommends shutting down parts of the power grid, and it's a false alarm, you've just caused a preventable outage and billions in economic damage. If it fails to predict a major storm, people will rightly ask why we trusted the machine. Then, there's the adversarial risk. If grid protective measures are automated and tied to AI forecasts, what happens if someone poisons the data? Solar data streams are generally trusted, but they're not immune to hacking. If an adversary could inject false data suggesting an imminent storm, they could trigger automated grid shutdowns. Alternatively, they could inject data suggesting calm conditions during an actual storm. Despite these challenges, AI is already changing how we do space weather science. Researchers are using machine learning to identify patterns in solar data, to predict CME arrival times, to improve magnetosphere models. The 2025 advances in multi-agent systems are accelerating this trend. We're moving from AI as a tool that augments human researchers to AI as an active participant. And that shift raises questions. If an AI system discovers a pattern that predicts extreme events, but the mechanism is opaque, a black box, do we trust it? Do we act on it? These are live debates right now, and they're directly relevant to AR4294. Because with all our advanced instruments, all our data, all our models, both human and AI, we still can't say with certainty what this sunspot will do. We can give probabilities, we can describe scenarios, but we can't predict. The sun is fundamentally complex, and complexity resists prediction. AR4294 is both a scientific event and a stress test for human institutions. It tests our models, our infrastructure, and the algorithms we trust. We have powerful tools, but the blind spots remain. The sun keeps secrets. Particles violate symmetries we didn't expect. And the AI systems we've built are themselves becoming complex, unpredictable black boxes we don't fully understand. And maybe that's okay. Maybe the lesson isn't that we need perfect models or flawless predictions. Maybe the lesson is that we need humility, resilience, and the wisdom to prepare for uncertainties we can't eliminate. We can harden our grids. We can improve our forecasting. But at the end of the day, we live in a cosmos that is vast and indifferent to our plans. The sun will do what the sun does. And when it points a loaded gun at us, as it's doing now with AR4294, all we can do is watch, measure, prepare, and hope. Because for all our science, for all our technology, we remain small creatures on a fragile world, utterly dependent on the stability of a star we can never fully control or predict.